Okay, I'm going to finish this up. So I started this code. This is the magnetic field due to a solenoid. So what I did was broke it into a number of rings right there, and then just calculate the magnetic field due to each one of these little pieces. What I want to do now is to make a visual representation of the magnetic field all over the place. And I'm going to leave this right here. I have 30 pieces per ring, and I have 1, 2, 3, 4, 5, 6. I have like 10 rings. Okay, so you can make as many rings you want, but this should be fine. So what we want to do, and I actually already have the code in here, but I'm going to leave that off there. What I want to do, like I've done many times, is just to make a grid of points in 3D. And at each one of those points, I'm going to calculate the magnetic field, and I'm going to make an arrow. That's all I'm going to do. Okay, so it shouldn't be too hard. So let's just jump down here. I already have that stuff. Let's just delete all this. I don't need that. And this is a different code, so don't worry, I'm not going to delete the old code. So the first thing, I'm going to use the same thing. How many steps do I want? And I'm going to use this as, I'm going to call this NS is 8. So I'm going to do 8 by 8 by 8. I find 8 by 8 by 8 works the best, but you know, you do you. Don't do 20 by 20 by 20 because you're multiplying all those together. Okay. And then I need to know the size of where I want to go. I'm going to call this, what should I call this? I'm going to call it capital S. Capital S, I want to go from, so the thing is L long. I want to go twice that length. So I'm going to go, this is 2L, right? That's the space of my stuff. And now I need ds, the step size. It's going to be S over NS. So how far do I go? And now let's just go ahead and make it. So I don't need to add a list. I'm just going to make the points. I'm going to make the points and then I'll make the arrows. So I'm going to start, R start is going to be the vector negative S over 2 plus ds over 2. So if I have these spaced out, if I add that space size, half of the space size, I'm going to be in the middle of the space. You don't have to do that. You can put the steps wherever you want, but I just think that works best. Negative S over 2 plus ds over 2, negative S over 2 plus ds over 2. Now I'm going to make 3 loops. While rs.z is less than S over 2, colon, watch your colon, while rs.y is less than S over 2, colon, while rs.x is less than S over 2, colon. And then again, up here, I need to reset my y value. rs.y is negative S over 2 plus ds over 2. And then down here, I need to reset my x. rs.x is equal to negative S over 2 plus ds over 2. So that's going to move. I'm just going to make spheres there for right now. So let's just make a sphere there. Position is going to be rs. Radius is going to be equal to S over 60. That should be fine. Now I need to move my rs value in the x direction. Rs equals rs plus vector ds 0, 0. Hopefully I don't make another endless loop. That's always embarrassing. Rs equals rs. I need to move in the y direction. Vector 0 ds 0. And then I need to move in the z direction. Rs plus vector 0, 0 ds. I feel like I've done this enough times that I shouldn't make a mistake, but you just never know. I did. 3 arguments. What line was that? Vector at line 42. 1, I just didn't put the comma. There you go. Okay, so there's my points that I'm going to calculate the magnetic field at. Okay, that looks pretty good. There's my ring inside of there. Okay, so now I don't want to put points, I want to put arrows. So let's put arrows instead. I'm going to just comment that out. So I'm going to put an arrow. The position is going to be the same, rs. The axis is going to be the magnetic field, which I have as a function, b, see right there, of rs. That's what I'm going to do. Now, I do need a b scale up here, so let's put b scale. No, I don't, because I'm going to plot not the axis. Oh, I still might need that. Yeah, so b scale equals 1. Yeah. So I'm going to plot the axis of b scale times norm of the magnetic field. That's that one. Yeah, that goes right there. Okay. And then I'm going to give it a color. Let's say color equals color dot magenta. So what does norm do? Magenta. So color, no, not color. Norm returns the unit vector for that vector. So I'm going to make all my arrows the same length. If you don't do that, you're going to have some that are ginormous and some that are super tiny. It just doesn't look. I like to do the norm. You don't have to, but B-scale tells me the length of all those arrows. So let's just see what it looks like. Oh, it's slow. See, that's too big. So let's make this B-scale a 0.01. Try that. That's perfect. Look at that. Pretty exciting. Zoom in a little bit. There's your screenshot right there. Look inside. Constant magnetic field. Look at that. Constant magnetic field. Outside, it looks like a dipole. Okay. Because it comes this way, it comes back around. Oof. So nice. Love it. Very excited. I just wanted to look at this. There you go. This is for your textbook here. Look at that. I can't stop zooming around. Look at that. How many times am I going to say look at that? Who knows? I'm thinking about, you could try for homework if you want, different colors, different spacing. You could try plotting the total magnetic field just to see what it looks like, and maybe you can get something that works. I'm not sure, but there you go. Oh, and if I end this video, I'm done with that. So it was a short video. Look, under 7 minutes. But there you go. Link to this code down below if you want to see the full derivation of the magnetic field due to solenoid. That's in my previous video. The whole playlist for my electrodynamics is down below. You should be able to find it there. That's it. Another video. Talk to you later.